Okay, so torque is a vector quantity that can be measured when a force is applied a certain distance from the fulcrum using a lever arm. So that was pretty wordy. So in this situation, we've got a balance beam. The beam is the lever arm. The fulcrum is the point of rotation where the beam attaches to the stand, right? And right now there's no force on that beam, right? But if I take one of these fire extinguishers, if I place it at the fulcrum, right? Oh, it doesn't let me place it at the fulcrum. But if I apply it to the left, it makes the beam rotate counterclockwise. If I sit it on the right side, it'll make the beam rotate clockwise, right? If I go a little farther out, the same thing happens, right? I'm on the left side, the force going down with a little white arrow causes rotation in the clockwise direction, and again on the right side in the counterclockwise direction. Now, if I put another mass that is equal on the opposite side, you notice it does not balance out. That's because the fire extinguisher on the right side is farther away from the fulcrum than the fire extinguisher on the left side. So there's actually more torque being generated from the fire extinguisher on the right than there is from the fire extinguisher on the left. And as a result, we see a rotation in the clockwise direction. Now, if I put the fire extinguisher exactly the same distance from the fulcrum, you see that the balance beam is balanced and we do not have rotation clockwise or counterclockwise. We have a balance of the torque, right? As soon as that distance on the right side is increased a little bit, we'll see the torque on the right side is bigger than the torque on the left, caused by the fire extinguisher on the left, and we'll see an imbalance. So what I'm going to do right now is show you how to do the math behind this situation. And we can use the math to predict what direction the balance beam will rotate, or to predict the placement of another object. For example, if I want to balance this beam with this 10 kilogram mass, if I put it the same distance to the fulcrum, it's going to have more torque. But if I move it a little bit closer, right, even though the force from the trash can is bigger, because the distance is less, now our torque balances out. So let's take a look at what that math looks like. So in this situation, we have these are supports, by the way, that will be removed. But if we draw a free body diagram of our balance beam, right, there's our point of rotation. There is a support right here. So if I say, there's a force going down due to the mass of the fire extinguisher, and right here there's another force, it's just as big going down. There is a reaction force, right, that's causing it, that doesn't let this balance beam go anywhere. Let's actually do the math on this. Okay, so we've got a mass of 10 kilograms multiplied by 9.8 meters per second squared. So we have 98 newtons of force coming down on the left, and the math on the right is exactly the same because the mass is exactly the same. The difference, right, is it's called the lever arm, the distance of the force to the fulcrum, right? So if I measure that distance right there, well, you guys aren't used to these engineering type drawings. If I just measure the distance right here, I get 1, 2, 3.5 units of measurement. Let's call those meters. 3.5 meters. And on the right side, 1, 2, my distance is 2 meters, right? So the formula for torque is force times distance, right? Torque is a vector, force is a vector, right? The distance is not. So on the left side, right, our torque is calculated. We have two torques. We have torque on the left, and I'll say torque on the right. So our force is 98 newtons, sorry, let's replace that with the formula. Force times distance plus force times distance. We have 98 newtons times a distance of 3.5 meters plus 98 newtons times 2 meters. Okay, the difference between these two torques is that one is positive and one is negative. This torque on the left is going to cause rotation in the counterclockwise direction, and on the right in the clockwise direction. So I'm going to assign a negative value to anything that's rotating counterclockwise and a positive value to anything rotating clockwise. So I'm going to throw a negative sign right here in front of this torque value. Make that one negative, and then do the math, and should get 98 times negative 1.5 by grouping those. 98 times 1.5. I get negative 147. Negative 147 Newton meters of torque, meaning, right, meaning that I'm going to get rotation in the counterclockwise direction. Now, if I go back to the lab over here, and I put those images back on, what do you have? 10 kilograms at 3.5. So 10 kilograms at 3.5, and then 10 kilograms at 2 meters, and then I remove the supports. I get rotation in the counterclockwise direction.